We have some announcements concerning midterm exam 1, which is coming up next week. And then we'll talk about Sir Isaac Newton's 3 laws of motion. And actually, we're going to do a little bit of review of homework and stuff. But before we do that, let me just remind you that the SI schedule is running. And Shai's around here somewhere. I guess she's still out in the hall. Tuesday today, 5 o'clock p.m. over, actually, classroom meeting 2. This is 207. Where's 212? I have no idea where that is. I wonder if that's a miss. Has anybody got it on their? I wonder if I misprinted that. It's possible. Shai will be here in a minute. We'll go back to that. Interesting quote from Galileo. I have never met a man so ignorant that I couldn't learn something from him. You know what that is? That's the virtue of what we call the virtue of humility in Galileo. And he was famous for being real feisty and competitive in his day. But he also was pretty humble about things. And that is actually a really good attitude to take as a scientist or as anything. So, by the way, whose birthday is it today? Anybody's? See, it's got to be somebody's birthday today in this room. Did you know if there's 22 people in a room, there's a 50-50 chance that one of those people has the birthday on that very day, supposedly. Anyway, let's talk about midterm exam 1. It'll be next Thursday right here. And get here at 10:30 sharp, if not sooner. Darianne and Caroline and I will be proctoring the test and trying to get you guys squared away. And a big class like this, it usually takes a little bit of time. So be ready to take that test. And then you'll have more time for it. It is a 50-question test. And usually that means, for me, a 50-question test, I give students 1 hour. I try to make it about 1 minute per question. So 50 questions, 60 minutes is just about right. Okay. Now, some of the questions are going to be on the iClicker, but most of them will be on this Raspberry colored Scantron. And I want you to try to get that as soon as possible. It's got the Pegasus logo on it. You can get them at the SGA office. And boy, there's a lot of people that sneak in this way here. It's interesting. Good eraser. Get one of those second grade jobs, you know, the little pink rectangles. You're going to feel like a dork until you make an error and you have to erase it, and your pencil doesn't erase well. And that's a problem. You don't want to get smudges, because if you smudge and you have the computer thinks you have 2 dots, and that automatically gets marked wrong. So you want to avoid that. Shai, can you verify this schedule? Is that the actual schedule today? And is it C, Classroom Building 212? Where is that? Because this is 207, and we're all the way at the end of the hall.
Oh, there's no. Let me check. That's what I have. If it's what you.
You haven't actually done this yet on Tuesday,
no.
the Tuesday session. What does it say? Whoa. I am way off. Say that again. Is that
That was last semester.
that's last semester? Okay, that's is that what it does it say?
Let me check the email.
Okay, let's just get this sorted out. Because you guys are going to want to start hitting SI this week if you haven't already. Did you have students yesterday? Good.
Nope, that's what I have. 212.
All right, room 212. It can't be on the other side of the, well, it's got to be somewhere. You'll have to find it. Okay, let's get back to exam prep. Okay, so you want to avoid smudges with your pencil and stuff. And every semester, especially in a class this big, there'll be students, they'll get a grade. You know, we get a printout of your answers and which ones are correct, which ones are incorrect. And a lot of people will have two answers and it gets marked incorrect. So you want to avoid that because that's like taking a point away from your test. Okay. iClicker 2, you're going to need one of these as well, just like in class. And what we'll do with this is type in usually calculations. So, you know, like 4.7 or something like that. And then you'll hit the send key. And we'll do some numeric answers with iClicker today to start practicing with that. Sometimes I give multiple choice, one or two, but usually it's a calculation or an alphanumeric question. And an alphanumeric question means you're typing in either letters or forming a short phrase, which you can do. You know, you can't type a sonnet, but you can, and you can't type a haiku. But you can maybe type one line of a haiku. So that's not too bad. But anyways, I'll show you how to do alphanumeric questions on Thursday this week. And then we'll do some more next Tuesday. Multiple choice, numeric, and alphanumeric. And then on Thursday, we'll take the test. Make sure your batteries are good. Don't let your batteries wimp out on you. If you bought it new this semester over at the bookstore, don't blame the bookstore. Blame the iClicker company. They load the clickers up with really, really low quality batteries. So if you're like totally paranoid about, you know, being in control of your test and stuff like that, just get some Energizers or Duracells and slap them in there. Because you don't, if your clicker fails in the middle of a test, that is pointage off your test. If it fails in lecture, that's not a big disaster, but on a test it would be. So make sure you check your batteries. Calculator. You can use a scientific calculator like this. Anything that has a square root should work. Scientific is way more than you need, but this was like 18 bucks at Walmart. I just checked the other day. And you may not use your cell phone for any reason, and that includes calculator. You may not use your cell phone calculator. And we had some students using a cell phone. We nabbed them last semester. So don't do that. And they failed the class, so it's not what you want to do. But just get one of these jobs at Walmart and you should be good. Questions about this? Scantron, iClicker, calculator. All right, let's keep going. Student was asking me, hey, Dr. B, what about formulas for the test? Do we have a formula sheet or what? Let me explain what you're going to have on a test. First thing you're going to see when you get the test, before you open it up, you'll see the cover page. The cover page is where you'll have your name and your PID, and you write it in neatly, of course, like all test papers. And then below that, there'll be an area where you'll have some information like the numbers in the back of the book or the appendix, you know, like the value of G, 9.8 meters per second squared, maybe a couple conversions from centimeters to meters, stuff like that. And so you'll have a little bit of that. You won't really have any formulas over there. For the formulas,
So I just looked and there is no room 212. So I'll email the.
wait a minute. Say that into the microphone here. Where's my microphone?
So I just looked and there's no room 212 on this floor for this building. So I'll be emailing some people right now, and hopefully they'll get back to me by lunchtime. Hopefully, if not, I'll stop by their office, and then if you guys just look into discussions, I'll let you know where it will be. But I'm 80% sure there will be a side today.
Okay. Thanks. Yeah, classroom building 2. This is classroom building 2. No, this is 2. Okay, this is 2. Or as they say in Rome, this is II. So check in discussions. Shai, see if you could email Sark right now, and if you have an answer by the end of class, we'll announce it, okay? Just let me know. Okay. So anyways, the cover page you'll have. So don't worry about memorizing, like 9.8 meters per second squared. I want to de-emphasize memorizing. Another thing that I do in terms of formulas is that the first page or so of the test, first 4 or 5 questions, you'll have a set of formulas and a set of concepts, and it'll be formula matching. And this is actually a PDF of the first page of exam 2 last semester. And here's a close-up of it. You can see that the first 4 questions are some energy formulas. And number 1 is actually the force law for universal gravitation. That actually might be on the exam next Thursday. We might actually get to that in a few days. But the way that you do this is you have these 4 formulas here, and then you have a bunch of concepts up here, and basically you just got to match them up. And so for this one, on your Scantron, you'd bubble in option E right there. Okay, and so that's how you would handle it. And that's equivalent, Alexis, to a formula sheet. But you get some points for, matching those up. And it's equivalent to a formula sheet in that you have all the formulas there, usually, that you need for the test. Occasionally, I'll write a simple formula in a question, as part of the question. But usually I'll put them in the matching area at the beginning of the test. And the reason I do that is to de-emphasize memorizing. For you guys, what I want is for you to be recognizing instead of memorizing. Right? That's a little bit a different task. And because I feel it's limited usefulness to memorize in this class, because I have a higher level task for you to do. And on exams, you will feel it. You'll feel the burn, as they say, on the exam. You will have to think. If you want to answer all the questions correctly and ace my test, you're going to have to really think. Memorizing is not going to help you a whole lot. Okay, maybe a little bit, but it's not worth making that your only study tool. It would be my last study tool because I don't memorize. I mean, there's certain things that you're going to know because you use them all the time, like 9.8 meters per second squared, or pi 3.14. So but if I don't memorize it, I don't expect you guys to memorize it. And a lot of guys in physics are like that. You just look stuff up, or you have something like this on a test, and it works pretty well. Now, questions about this formula matching? Go ahead.
So no matter what on the test, like any formula we're going to need is going to be on this page?
Any formula that you need is going to be on the test, usually in the first 4 or 5, maybe 6 questions of matching. But sometimes I'll put it on like number 31. I'll insert a formula in problem number 31 that you need for that problem. So on problem 31, I might say, as you know, Newton's second law is F equals ma, and therefore, and then I give you a question. Okay, so I might do that, but it just depends on. Most of them are going to be in here. Question. Are the test questions similar to homework questions? I cannot answer you that question because I'm not going to tell you what's on the test, but you might find that studying the homework and really knowing the homework questions is going to lead to happiness on exam day. I'll just put it that way. But, but don't memorize the homework. All right? People do that, and it's, you know, you're not going to be, if you're going to, it's going to be like mental constipation. You're going to have all this stuff jammed into your head, and you can't get it out because I'm asking you to do something else. I'm asking you to think. Okay, so it's going to be cluttering up your brain. So don't do that. But use it to study. And here's something else that I'll just mention, and I'll keep mentioning it. This is one of the reasons that SI, which you should all be going to, if we can figure out the schedule. One of the reasons SI. Can you move forward, please, into the first 7 rows? Yeah. SI helps you make friends. And it's always, in Mr. Rogers' neighborhoods, it's nice to be friends and all that stuff. But in this class, it's good to have friends to study with because it forces you to talk with each other, and that forces you to think about the subject matter at hand. And that is going to help you work more rapidly. If you can think things through the night before or 2 nights before in your study sessions with your study partner or an SI and really get it locked, really get a good feel for it, you're going to work a lot more quickly on exam day. And so, as I always say, try to find a study partner. And if your study partner is a slacker, find somebody else. So you don't feel like you have to permanently have a study partner. Okay. Any other questions about that stuff, matching and so forth? Okay, let's keep going. I'll give you a little bit more information on the exam next Tuesday. And the exam will be over everything from the first day of class, physics-wise. I mean, I'm not going to give you questions about the syllabus, but physics stuff from the very first day all the way up to Tuesday next week. I'll have office hours tomorrow and next Wednesday, 10:30 a.m. to noon for this class. And that is in the Physical Sciences building, room 158, PS 158. You go in the main door and then you turn left, and it's right there. So stop by and we'll just, we'll talk. We'll work on calculations maybe or clear up concepts. And that's how Shai, she's the SI leader. She came faithfully every week, she and her 3 companions, and she did really, really good. And she got a really great exam grade, started getting really good exam grades, and a great semester grade as well. All right. Questions about office hours? Okay, let's keep going. I want to talk about distance polygons and kind of wrap that up. I shouldn't say wrap it up. We're going to be seeing the distance polygon concept until the cows come home this semester because, we're physics class. So last time we talked about the distance triangle for drop distance. Here's the generic one for you know, some other accelerated system that starts from rest. If you start from rest and you have a positive acceleration, this will show you the distance that you cover. If you drop something from the top of the library, the first formula will tell you how far it drops in a certain amount of time. And in parentheses in the first box there at the top, up here, it says drop distance, parentheses, VI equals 0. That means initial speed is 0. In other words, you're holding it. You're not throwing it downward. Now, you can do that. There's a different formula for that, and we can handle that. But this is one for it's just, it's just you dropping, a water balloon on your buddy or something like that. Okay, and these are the distance triangle. This is what they look like in formula. Okay, the velocity graph shows a triangle, and the formulas come up with 1/2 times the acceleration times the time of acceleration, the amount of time you're accelerating to the second power. Now, I want to show you another formula, and this is a position formula, so it's a little bit different. This one is one where you're actually trying to plot a specific position. So it's a little bit different from a drop distance formula. And this is one for constant speed. Acceleration is equal to 0. You have the final position x subscript f equal to the initial position plus whatever you get here from a distance rectangle. Okay? And so this term here is just the initial speed, v subscript I, times the amount of time that you're moving at that speed. So that's t here is the width of the rectangle, the distance rectangle. And x subscript I is the initial position. So if you start if you're at, x equals 5.3 meters, so that's over here to the right a little bit, and then you start moving at 1 meter per second, you'd use this formula with x subscript I equal to 5.3 meters. X subscript I equal to negative 5.3 meters or negative 4.2 would be initial position over here. If VI is negative, that means, as usual, you're going to the left. All right, so in this formula, this one is used to keep track of left and right position. The leftness, make a note of it, leftness in this formula is denoted with minus signs. So if my initial speed is 20 miles per hour and I'm going left, I would have negative 20 in there for VI. If my initial position was 12 meters to the left, that would be x subscript I equal to negative 12 meters. All right, and so this position here, just a little extra emphasis there. Now I'm going to ask you a iClicker question. So get your iClicker out and get ready to. We have a bunch of iClicker today, so hopefully you're squared away on the iClicker. And we are operating on frequency BB. So if this is the first time with your iClicker, which I expect for some of you it is, you hold the power button down until you get the flashing square, and then you type in the letter B twice. And that'll get you the go nitro message and then the ready message. All right. Now here's your brain burner question. And I want you to really think about this one carefully. Assume positive V means rightward as usual. Go ahead and vote when you have a decision. See, this one's making you think. See how quiet it got in here? Everybody's thinking. They're reading carefully and they're thinking carefully. Now, when you guys are in class like this and we're working on questions, I definitely want you to talk to your neighbor. So while we're actually running the question, until I go the countdown to 0 and then stop it, definitely talk to your neighbor, consult, and that's another interaction that will help you think if you have a neighbor that is friendly. If they're not friendly, good. See, this is lovely. I see people pointing at the board and gesturing, and I see somebody. This is great. And you could change your answer if you want. "30 seconds. Now, on exam day, you can't be blabbing with your neighbor, but in lecture, yep, I want that. I love it. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Well, we've got 166 people voting, and that is, we still got 60 of you that are not voting. That is not good. This is the first official day of clicking, and you're gonna, if you don't have your clicker, you're gonna start missing out on stuff. Right? You better get yourself squared away. All right, let's see what we got here. What? What? Oh, you guys are geniuses. I thought that was a brain burner. Yeah, none of those polygons. And why is that? Because I use the word slowing down. The only thing in this diagram that signifies any kind of acceleration is polygon W, but that's speeding up, not slowing down. And that's because it's going from 1 meter per second all the way up to 3. Now, I have another calculation question for you now. So hit the refresh key, because this next one is going to be numeric answer. Okay, so hit refresh, and that'll allow you to type in numbers. Now, the way that this works is you use the up and down arrow keys. I believe it starts you on the letter A. Is that correct? And then go, I think the numbers are down below that. So use the down arrow key. And I just want a single number, whole number. So no decimal points today. We'll try decimal points on Thursday, I think. Maybe we'll do some decimal points today. Delta V. "15 seconds. Oh, wait a minute. This is calculation. I'll give you a minute. And this one you don't really need a calculator to do. Just use the... young lady with the baseball hat, can you move forward, please? Yeah, we want people in the first 7 rows or... Yeah, anywhere is good. There's some seats up front here if you want. The final, the initial. Okay, 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Stop. And actually, this is interesting. This is how the numeric results look. Okay, it's kind of sideways. A lot of people voted for 2. A few people voted for 1. A few for 0. A few for 3. One person voted for 20. Don't laugh. I'm not laughing. I'm not doing that to make any humor. I'm just pointing out what people have got. And the correct answer is 2. Now, if you got that right, I still want you to make a note. Did you write a sketch of this in your notes? You should. My side note for this problem is the delta V is the height of a velocity triangle, which in this case is 2 meters per second. Next question, and you don't have to hit the refresh key. It's another calculation question. Oh, what's your first name again? Brittany, okay. Delta V is the height of, if you think about it, it's the height of a velocity triangle. Because if it's not a triangle, it's not changing. It's either a triangle like this, positive acceleration, or a triangle like this, slowing down. But the delta V is always going to be the height of a triangle. Otherwise, you've got a rectangle, and there's no delta V for a rectangle. Okay, next question. What is the acceleration? Same time interval. And you might have a question like this on the exam. Alexis, you might, so I might ask you to type in an acceleration on the test. So like question number 48 for 2 points, or 47 for 2 points, By the way, the Scantron questions will number 40 something, and then all the other points will come out of the clicking and stuff. Shai, how you doing back there? You got some information? All right. Do you want to announce it right now? No, come on up to the front. Okay, Shai has an announcement. Brittany.
So I just emailed my supervisor, and it was just a mix-up. It's actually classroom building 1, not classroom building 2. So same room, different building.
Okay, so CB1, room
212.
212. All right, and I'll change that. And make a note of that, CB1, room 212. Is the time correct?
Yes, they're
Okay.
gonna send me a different schedule.
Okay.
Just with the different rooms.
All right, good. All right, so we'll try to get all this reorganized and stuff, but for today, we're good. And Shai, was the Wednesday, you have a Wednesday, right? Was that one accurate? Okay. All right, so it looks like that schedule, the only one that was inaccurate was Tuesday. Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop. And okay, this one, we have a mixture of results on this one as well. Some of you voted for 1, some of you voted for 2, and if you voted for 1, you are correct. The reason for this, go ahead and write it down. It's not on the slide, but you can jot it down. The acceleration is delta v over delta t. The numerator is 2 meters per second. Delta t is the width of the velocity triangle. So Brittany, whenever you have acceleration, you've got a triangle of some kind. It's going to have a width, that's your delta t, and it's going to have a height. Okay, and that's going to be delta v. Now, if you go back to high school geometry class and you remember the definition of slope, rise over run, this is a positive slope, and the delta v is positive. If we had a velocity graph like this that was coming down as it went from left to right, then that would be a decrease in height for a positive increase in time, and that would be a negative slope. So that's something to think about and remember, delta V over delta T. All right, so if you got that one wrong, make a note of that, and hopefully next time I ask you some questions, you'll be squared away. I want to do some more elaborate formulas for positions that accommodate acceleration. The first two acceleration formulas we have, those are distance formulas. They're not really position. You can use them to make a position formula, and we will do that right now. Now, this is the generic position for constant speed. We talked about that already. This right here is a distance rectangle. The first equation that accommodates acceleration is this one. In this formula, you have all of the constant speed formula. If you look at it, it's the same here. But then it also has a distance triangle out here, 1/2 at squared. Now this is for a generic horizontal acceleration. And this term here, VIX, V subscript IX, that does not mean Roman numeral 9. What it means is the initial velocity's x component. This is the formula for the x position at some later time t subscript f. It's related to the initial conditions, which are xi and vix, and the equation, the time evolution part of the equation, 1/2 at squared. So this one, this is a position formula. And again, in this one, if you have leftness, it's an x equation. So if we consider this to be the x-axis, left and right across the front of the room, then leftness is associated with a negative number, and you would put in, like if you have a leftward acceleration, you'd put a negative 2.5 meters per second squared or whatever it was. And if you have a leftward initial velocity, same. Negative 7.1 meters per second. And if you have an initial position, x subscript I, over here on this side of the room, well, that's all right. That's a negative 2.4 or whatever it is, meters. All right. Now, the next formula is going to look just like it, but this one is specialized for free fall. So this is the vertical form of the same equation. And in this one, we have the symbol g to represent the free fall acceleration at the surface of Earth. From the top of Mount Everest, where it's pretty close to 9.8 exactly, all the way down to the bottom of the Mariana Trench in the deepest part of the Pacific Ocean, it's 9.8. And there are variations of it, plus or minus 0.01 or so, 0.001. And we can measure those with really sensitive equipment. But for us, it's negative, it's 9.8. And in this particular formula, hopefully it looks very similar to you. Again, we have initial velocity. And hey, you guys, this is the initial velocity in the y direction. So if you have something that, in other words, if you throw a baseball straight up in the air, with 20 meters per second of upward speed to start, this is your formula. And with it, you could figure out any position at any later time t. Also, because we're trying to keep track of up versus down, downward means negative, and therefore, in this one, you must use negative 9.8 meters per second squared. Now, we're going to use that in a few minutes, and it's important, especially in this one, because we care about up and down. So if you care about left and right, if you care about up and down, which if you're trying to map out a position, for any moment of time t, you do care about that. You've got to use your minus signs carefully. And we'll work through some examples in homework and then on Thursday to give you some practice with this. Question? You mean this one and this one? The question was, in a problem on homework, how do you distinguish from the context? Do you use the drop distance formula or do you use this more deluxe thing down here? The answer to that is you have to read carefully. And on the exam, I'm going to nag you like your mother-in-law. A mother-in-law from another planet, baby. I'm going to nag you to read carefully and think carefully. And if you read carefully, the context will tell you if you're trying to figure out a position or if you're just trying to find how far something falls. Like when Peregrine dropped the rock down the well. How far does it go? But he could have done this one. What is its position relative to the top of the well, or relative to the top of the mountain, or relative to the top level of Moria, or relative to the bottom level of Moria. He could have used this. And each version of that would be a different version of this equation, but they'd be cousins of each other. So the context will tell you if you read carefully. And you guys, I'll just make a side note here that, I don't know, if you ask a student from last semester or any of my previous semesters, they may say, Dr. B, let me say what I want to say first. I try not to write trick questions. I hate trick questions myself. And so I'm never going to deliberately. Now, sometimes I'll write a question and I'll think, and like sometimes when I'm editing a question and changing a 2 for a 7 or a negative sign for a positive sign, sometimes I'll bloop it up. I'll have a blooper in there and it'll blow up in my face. But never intentionally am I going to write a question that is difficult because it's tricky. It's just going to be difficult because it's an honest question. And I'm going to try to make questions that if you think, you'll be, on a multiple choice anyways, you'll be able to eliminate at least one or two of the options. Which is the way to do it? If you get stumped, they always say on a multiple choice test, try to eliminate one or two if you can, and then make an educated guess with the leftovers. And a lot of my questions, you'll see that if you think about them carefully, there's only one answer. They may be tempting, but only one of them is a rock solid lock. Okay, so I'm never going to be writing trick questions. I hate them. And hopefully any student of mine from the past will agree with me that no, Dr. B doesn't write trick questions. Anyways, I try not to. And I want you to remember that. Okay, because I want you to think. Thinking is hard enough without me, like making a, like a brain teaser. As I was walking to St. Ives, that puzzle? I saw a man with 7 wives. Each wife had 7 sacks. In each sack were 7 cats. How far was it to St. Ives? So they, you get all this numerical information and they ask you something completely different. Now that's a brain teaser. And I try not to do questions like that. But I do expect you to read carefully. So don't think you're ever going to get off the hook from that. All right, let's look at the distance triangles. Here are where the distance triangles show up in your list of formulas. And then here's the little slab of distance rectangle stuff. And that's about it for most of physics. It's either rectangles or triangles. And the guy that figured all this stuff out, and from which even NASA runs its computer simulations, is Sir Isaac Newton. In other words, you don't have to have the rate of change of the acceleration. All you have to know is the acceleration, and then apply formulas like this. Now, here's an application area that's very important, a ballistic trajectory. Ballistic means to throw in Greek. If you throw an arrow, or the bow throws an arrow, or if a cannon throws a cannonball towards an enemy ship, you want to know where it's going to land. Hopefully it'll destroy your enemy. And you want to know how long it's going to take to get there. And the way that you handle that with these simple equations that we just listed is you use the first formula for x position. xf equals xi plus vix times t. And then you use the free fall y subscript f formula. And you combine them together to actually plot out a ballistic trajectory. Now go ahead and make a sketch of this woman shooting an arrow. And this is kind of a wimpy arrow because a real arrow is going to go a long distance before it hits the ground. This was kind of pokey. But go ahead and draw an arc. That's a parabola, which we'll have more to speak about on Thursday. And I'm going to select a point out here, right about there. Just go ahead and put a point. Pick a point, any point, somewhere out here on the parabola. And here's what I mean by using the 2 formulas. The x and y coordinates are computed at any time t using those formulas. If you know the initial condition, the position, and velocity, you can, and then at any time t, you can figure out the position. Because we know what g is, 9.8 meters per second squared, negative. And so if you know its initial, so if you know the velocity, if you know the position here, like about 1.5 meters above the floor, and x coordinate 0. That might be a good way to do it. And then initial velocity, 14.5 meters per second straight ahead for this arrow anyways. Then you can figure out the coordinates at any time. Same thing here with the football player. Okay? Tom Brady. Crushed. Yes! So, I was getting really nervous at the end of that game, but they beat him. Who votes for, in the Super Bowl, who votes for the Panthers? Who votes for the Broncos? Ooh, that's a pretty even split. I'm going with the Broncos. I think the Broncos are going to take it, but we'll have to see. Anyway, for this guy, here's the concept you want to remember for this one. This is a ballistic trajectory. He's starting with some horizontal speed, just like the bow and arrow lady, but also some upward speed. So he's throwing it up. He's arcing it down the field. Okay? So this is like Brett Favre throwing it 60 yards down the field without even breaking a sweat, or A-Rod, or Tom Brady, the crybaby. But on this one, if you neglect air resistance, these blue horizontal arrows are always the same size. All right, that's what it means. So you're always matriculating down the field, horizontally anyways, at whatever your launch speed is, your horizontal component, your horizontal blue arrow is, whether it's 20 meters per second or 30 or what, it's never changing if you neglect air resistance. But notice the vertical arrows, he starts with some upward velocity here. A little bit later, whoa, he's lost some. At the very top of the arc, and go ahead and make a note of this one, the top of the arc, the vertical component is completely vanished for that precise point only. Because as soon as he goes past that, which he does, he's going to start getting downward velocity. It's coming back to Earth. And here's the receiver out here trying to catch the ball. All right? And you may want to ask yourself this particular question. Well, why is it that velocity is a constant? I mean, the horizontal velocity anyways. Why is that? The vertical velocity is changing. The vertical velocity component is changing. But what about the horizontal? Why doesn't that change if you neglect air resistance? Well, here's the reason. It's because gravity is only vertical. And another way that I like to say this is that gravity is vertical. It'll only affect the horizontal component of the motion, it'll only affect the vertical component of the motion. So his vertical blue arrows here are changing for each second that the ball's in the air. But gravity does not act horizontally. There's no such thing as horizontal gravity. And so because of that, because there's no such thing as horizontal gravity, those horizontal arrows, they just kind of stay at 20 meters per second all the way through. And I'm going to give you some homework problems and probably Thursday work on some more of these ballistic trajectories. We'll work with some of the speeds and some of the components, and we'll do a realistic example of like a baseball heading out to the outfield or something like that. And remember for this one, it's because there's no horizontal change in the motion. The horizontal arrows are the same because gravity only acts vertically. And that being the case, we'd better start thinking about forces. And to do that, we've got to start with Sir Isaac Newton's 3 laws of motion. NASA sends men to the moon and brings them safely back to the Earth. It's not easy, but they do it. And they follow Sir Isaac Newton's laws of motion. So let's go ahead and get an idea of his 3 laws of motion. And actually, the first law of motion was developed by Galileo. And you can read about it in chapter 2 of the e-text, which I carefully wrote for this class. Galileo used the idea of indifference, that an object on a horizontal surface that has no friction, theoretically, will be indifferent to being at rest or at constant velocity. Now, the way that Sir Isaac Newton said it was this: every object retains its state of rest or its state of uniform straight line motion unless acted upon by an unbalanced force. So theoretically, if you're on a skating rink, and skating rinks are pretty darn close to no friction. I mean, if you have a good pair of ice skates anyways. You know, if your ice skates are good and sharp and you don't fall on your keister, you can go a long way on an ice rink. You know, somebody gives you a push and you just keep on going until you get to the other side. All right? That's kind of like what this is. Now, the way to change that, the only way, you know, so if you're on an ice rink and you go all the way to the other side, how do you change your state of motion? You experience the force of the side of the ice rink on the other side. You know, it's rigid. Okay, you can't make a wall of an ice rink out of water. It's no rigidity. So if you have a wall around the ice rink, you know, like they do at any kind of hockey game, it's going to be fairly rigid, and that provides the unbalanced force, an external force that stops you. So let's think of an example here. An apple in the apple tree has a pair of balanced forces. All right. The stem attaches to the branch, and the stem is pulling upward. Okay. And then, of course, gravitational weight force pulls downward, and they balance if it stays stable, if it doesn't, you know, start to fall. But if the stem weakens, you know, like it dries out, and eventually, you know, an apple will fall, you know, later in the autumn. Same thing with oranges and stuff, any kind of fruit. The balance fails and down it goes. And so then it's no longer at a state of rest, but in a state of free fall acceleration. All right? So law of motion number 1 describes the fact that you'll keep at rest or you'll keep in constant velocity if there's no external force acting on you that's not balanced. Okay? Now, on an ice skating rink, I want you to make some notes. This is not in the lecture, but I want you to make a few notes about the ice skating rink, this mythical frictionless ice skating rink to which every skating rink aspires. The mythical frictionless ice skating rink, you'll keep going across the ice as long as you have ice. Okay? And the mythical frictionless ice skating rink is infinite. So you're just going to keep going on this ice skating rink. But is it true that there are no forces acting on you on the mythical frictionless ice skating rink? Is there a force? What's your name? Yeah. Maria? You say that there's a force? What force is acting on you? Yeah, gravity. If you're on the skating rink, you know, gravity's pulling you downward. I mean, you're on the planet Earth, right? And it's a mythical, but I mean, you still have good old gravity. And then, but how come you don't start dipping downward? Fellas, you're right in front of me and you're talking the entire class. All right? I consider it rude and distracting. Now stop screwing around. All right? Or go sit out in the hall if you want to chit-chat. I don't like it. All right? Especially right in front of my face. All right. Now, so we've got gravity on this, you know, so gravity, but how come you don't, you know, free fall down? How come you're not in free fall? Yeah, the ice provides you with some upward force. So students, the two forces acting on you, there are two external forces acting, gravity and the rigidity force of the ice. Every molecule of water in the ice bonds with its neighbors to form ice crystals. And those crystals are pretty rigid. They'll flex a little bit. And they're actually like little trampolines. And so, if you're on a trampoline, you'll sink downward a little bit. And the trampoline is trying to pull you back up. It's kind of like rubber bands pulling you back upward. And ice is like, any surface is like that if it's rigid. The molecules in a rigid material are like little trampoline. The network of molecules on the surface is like a big old trampoline. It doesn't really give that much, and it can be broken. So if you put an elephant on this desk, it'll crush the desk. But just about anything else, this desk is nice and solid. Okay, and that's because the trampolines hold together. Let's keep going. About mass. Mass. Kilograms. This is the quantity that encodes the inertia. So if we say something has inertia, and all right, how can you measure the inertia? Well, the way that you do it is by using a balance. Okay, and it's the quantity that if you have more of it, it means it's harder to change your state of motion, your dynamical state. So if you have a kilogram of mass, it's easy to change your dynamical state. You can accelerate. But if you have 1,000 kilograms of mass, that's a metric ton, it's really tough to change your dynamical state. All right? Now, the mass is measured in kilogram, as you know. And here's how we figure all this out. Now, if you've read the first chapter in the introduction, and hopefully you're reading into chapter 2. You'll have read about a gram and a kilogram. Gram is a cubic centimeter of liquid water. And the way that it works is you take your unknown object and you try to balance it with like a liter of water. So here's a basketball in the balance. Okay? And the basketball is less than 1 kilogram. So the kilogram of water is going to win the seesaw battle. And so it's going to be on the low end of this. Anyways, you figure out the number of kilograms of water or grams, of water. And then that's the same number of grams in your object when they balance. So this diagram here, they're out of balance. Okay, because a kilogram of water is heavier than a basketball. Right? No matter if you're on Earth or on the moon, anything like that, you're going to get the same number of kilograms to balance. Okay? Now, for a basketball, it's about 0.6 kilograms. So that'd be about 600 grams, 600 cubic centimeters of water. Right? So for basketball, you can't use liter bottles. But for bigger things like people, trucks, elephants, yeah, liter bottles of water would work if you have a big enough scale. Balance. And so this is the idea of mass. And for this reason, if you're up on the moon, do you ever remember that joke when you're like third grade? You go to your buddy and you say, okay, what's heavier, a ton of bricks or a ton of feathers? Do you ever remember that from when you were little? And the answer is neither. They're the same because they're both a ton. So they have the same mass. They'll balance each other in a balance. 1 metric ton versus 1 metric ton. But of course, a ton of bricks feels a lot heavier. But all right, diagram. Let's look at this diagram. So you're in a bus. And in chapter 1, I believe, chapter 2, I have a discussion about buses and the UCF shuttle bus. So if you're in the UCF shuttle bus and you accelerate forward, if the bus accelerates forward and you're not stabilized, you're going to pitch backwards, all right? You're going to fall on your you-know-what. Okay, if you're in the shuttle bus and it's in a state of motion at 20 miles per hour or something, straight line, and you're standing in the aisle and it stops, if you're not stabilized, you're going to face plant in the aisle. You're going to fall forward, all right? You're going to look like a total klutz. Same thing if it turns left and right. Okay, now this one, the bus is turning to the right from this overhead view, and you're going to keep going. Your body wants to keep going straight. So what that does, if the bus is going this way, it's going to feel like you're being thrown into the seats to the left of you. So you're going to bump your hip over here on the right, unless you stabilize. And when you are on the bus, they have all those bars and straps and things to stabilize you, just because of this law of inertia. All right, so riding on the bus, you stabilize forwards, fore and aft, port and starboard. Unless you're on a mythical bus that never changes its speed or its direction. But I don't really know any buses that actually are used for that purpose, so you're basically going to have to stabilize yourself. Okay, and let's keep going. Here's the same thing. Distinguishing forward and back and left and right is the key to understanding this particular trajectory. The bus has forward or backwards component to its motion, unless it's like a hover converted bus, so they can fly through the sky. But if it's on the ground, it's on the streets, it can either go forward and back, left or right, or a mixture of those. A little bit to the left and a little bit forward, or a little bit left and a little bit back, for backing up. Okay, it's the same thing with this particular trajectory. The law of inertia allows you to split the motion into perpendicular components like this and analyze it the way Galileo did. Galileo was the first one to figure out exactly what was happening with a projectile, like a baseball. And he was trying to figure out a cannonball. Where does a cannonball fly when it's launched from a cannon? Because he was in the employ of the Grand Duke of Venice. And the Grand Duke of Venice had a navy, a big one. They were a big mercantile trading empire in the days of Galileo, and which the days of Galileo were also approximately the days of Shakespeare. And so that play, The Merchant of Venice? Yeah. That's what the Duke of Venice, big mercantile empire. So he's trying to figure that out for the Duke, so his navy could be a good navy. Second law. All right, first law tells you about no unbalanced forces, what happens. No forces or no unbalanced forces. So either you're way out in space and there's no force acting on you, or you're on the mythical frictionless ice skating rink and no unbalanced forces acting on you. So what happens if you do have some unbalanced forces? Well, first thing that you do is you add up all the forces, and if anything doesn't balance, then you call that the net force. All right? And the notation for that is F subscript net. Now, here's a picture of some forces exerted by Dwight Howard and LeBron James. And let's say that Dwight Howard exerts 100 units of force to the right, and that his main basketball enemy, LeBron James, exerts 80 newtons to the left. In other words, negative 80. Well, as I said up here, you add up all the forces. 100 plus a negative 80 is equal to 20, positive. And that means that the net force is 20 units of force to the right. Sir Isaac Newton said, okay, get your net force in a manner like this. And if you're working in 2 or 3 dimensions, maybe use the Pythagorean theorem a little bit. But if it's left and right, up and down, it's pretty simple. Positives and negatives. And then he said, the more push you have, the more acceleration you get. And he said, the more kilograms of mass you have, the less acceleration you have. So like we said, the more inertia you have, the harder it is to accelerate you, to change your dynamical state. Now, if you think about it, big mass, small acceleration means if there's a formula for acceleration, the mass has to be in the denominator. The force, the push force, or pull force, has to be in the numerator. And so this is the actual formula. A is equal to net force divided by mass. And here it is in the outline. Here it is over here as a graphic in white. Net force over mass is equal to the acceleration. And another way to write that same equation, but from the viewpoint of the net force, is F net equals ma. And here's a big version of that. Now that's Newton's second law, F equals ma. And a lot of times, if you were to dissect the brain of an engineering student, you'd see a big portion of their brain was dedicated to the concept of F equals ma. You just use it all the time. And hey, you guys, we're never going to stop talking about F equals ma. We're learning about it today. It's going to be on exam 1, but it's also going to be on exam 2 and exam 3 and the final. It's going to be on any physics test. So hit refresh again. Let's do another multiple choice question. See how things work out. And let me get a multiple choice. Whenever you change from multiple choice to numeric or back, you have to hit the refresh key. So turn your clicker on and hit the refresh. And try this question. Using F equals ma. F equals ma. F equals ma, a mass times an acceleration. The magnitude is not hard, but what are the units of a mass times an acceleration? 20 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Aha. A little bit of disagreement here. But let's take a look at it. Here's the answer. A kilogram meter per second squared, or kilogram meter per second per second. That is the official unit of force in the metric system. It's called the Newton, after Sir Isaac Newton. The symbol for the Newton is capital N. So a force of 1 Newton accelerates a 1 kilogram object at the rate of 1 meter per second squared. That's the metric unit of force. Now, I'm going to ask you a tougher question involving a dinosaur. And I want you to it's going to be a calculation, so hit the refresh button again. You see it up there, the blue refresh button. And let's do a numeric question. Calculate the weight force of a 342 kilogram T-Rex. Use their surface gravity, G. 9 point. Now, on this one, all I want is the magnitude. We know it's downward, so you don't have to put a minus sign in there. So just give me the number. And give me to the nearest Newton. If you please. F equals ma, except instead of A, generic, we use G, 9.8. So the weight force is mg. And I better do this when I can't remember what the answer is. Okay, let's see what we got here. Oh, there you go. All right, go ahead and try it again. Hit the refresh key and try to type in your number. I'll give you another minute. Uh-oh, don't round off, or round off carefully. And don't use, you shouldn't be using a decimal point. You should be rounding off. Don't use a minus sign. Get that minus sign out of there. We know it's downward. Just give me the magnitude. Okay, 30 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys voted for here. Uh-oh, we got a problem. It's not. I'm not going to show you the stats. But I will tell you that the correct answer is 3352. Raise your hand if you got that. 33. Geniuses! All right. So on that note, let me dismiss you. And I'll see you on Thursday. There'll be some homework tonight, homework 5. Be ready for it by supper time, if not sooner. You're dismissed, 11:49.